Assalamualaikum. Today we will present our assignment with title F-Spectral clusters. Introduction of F-Spectral clusters. An F-type mean sequence star is a hydrogen-fusing mean sequence star with spectral type F and luminosity class P. F-type stars are mean sequence stars that convert hydrogen into helium or carbon. After converting all of the hydrogen, they proceed to the following stage by converting the helium as well as carbon. Following the main sequence, outer pressures will exceed inward pressures and the star will begin to develop. The next hottest class of stars after the Sun's class of G-type stars are the F-type stars. These stars have surface temperature about 6,000 and 7,600 K and masses that range around 1.0 to 1.4 times that of the Sun. When seen by the atmospheres, the star's temperature range gives them a yellow-white appearance. This class of star might alternatively be referred to as a yellow-white dwarf, since a main sequence star was known as a dwarf star. Example of F-spectral clusters. First, Polaris, the North Star. An F-type star was among the most well-known stars in the night sky. It is one of the most significant because it is the star that several travelers used to navigate in the past. Since the star is exactly above the North Pole, recognizing it can help travelers find their destination. People in the southern side will not be able to see it because it is the northernmost star. To guide themselves, they will need to use a separate star and constellation. Polaris is a multiple star system, thus there is little likelihood of a planet around it. Planets have been identified in binary star systems like algebra. The system stars are all F-type stars with varied size. Figure 1 depicts Polaris, also known as the North Star. Properties of F-spectral clusters. The temperature of an F-type star can range from 6,000 to 7,500 Kelvin, while the Sun's temperature is approximately 5,778 Kelvin. They are between 1 and 4 times as big as our star, in addition to having greater temperatures. A star's lifespan would be less than the Sun's, since it is slightly larger than the Sun. A star's fuel consumption would be increasingly uneconomical, and its lifespan would be shorter as its mass increases. The star will still live for billions of years, but it will not be as long as the Sun, who is estimated 10 billion year life cycle. It is already halfway through. There are fewer of them in the universe as a star's mass increases. For instance, M-form red dwarf stars, such as Proxima Centauri, are the most prevalent type of star in the universe. 3% of the stars in the Milky Way are F-type stars, compared to 7% for G-class and 12% for K-class. The mass and radius of a typical class F star are 1.2, which is in range 1.04 until 1.4 solar masses, and 1.3 until 1.4 solar radii, respectively. The F cluster has a surface temperature of 6,750 Kelvin, which is in the range 6,000 K until 7,500 Kelvin, a brightness of 3, which is 1.5 to 5 solar luminosities, and a lifetime of 5 billion years. Table 1 illustrates the spectral clusters with the F-spectral type highlighted. Table 2 lists the F-type main sequence stars properties, including its mass, radius, luminosities, temperature, and color index.
So next, I will explain about the life cycle of an F-spectral cluster. Next, about the F-cluster origin. Firstly, a star life cycle may be broken down into many clearly defined stages. Stars are created during the initial phase of their lifetime by the gravitational collapse of enormous clouds of gas and dust known as nebula. Their life cycle begins at this point. Then, the gravitational collapse of a nebula produces a protostar. It is a star formative stage. Then, the developing star attempts to achieve a balance between its internal forces and gravity during this period. A protostar begins quite brightly. It may have a diameter of billions of kilometers. Typically, it lasts 100,000 years. The protostar spins extremely quickly at this time, creating immense heat and pressure that causes the gas cloud to further contract. The star is born when the temperature hits roughly 10 million Kelvin, at which point hydrogen fusion may take place. So, lastly, the protostar experiences a phase known as the T-Tauri phase just before fusion starts. The core temperatures are now too low for hydrogen fusion. Therefore, the primary source of energy for stars is their gravitational pull. At this time, the star resembles a low to medium mass star in size. It is, however, much brighter. This time frame, which may last up to 100 million years, is a period during which a star brightness varies as it attempts to balance its internal and gravitational forces. Next, for F-class star life. The main sequence refers to the time in star's existence when its core may fuse hydrogen. A star spends 90% of its life in this stage. The main sequence stars come in a wide range of masses, hues, and luminosities. A star's mass directly affects how long it stays on the main sequence. Average stars like the Sun spend billions of years on the main sequence. Since the universe creation, none of the tiny stars, the red dwarf, have departed the main sequence because they consume their hydrogen resources so slowly. Nuclear radiation production stops after a star's core has completely fused all of the hydrogens. As a result, the star begins to collapse owing to gravity once more. The heat from this collapse raises the core to a temperature where the hydrogen in the stellar atmosphere can burn. The star outer layers enlarge as a result of this process, cooled to just 2500 to 3500 Kelvin and turn redder. A star can grow to a size between 100 and 1000 times that of the Sun during this stage of its existence, which can last up to a billion years. Next, for F-class star and or death. The star core is now hot enough for helium fusion to occur as it continues to heat up, reaching temperatures of up 100 million Kelvin. The core of tiny and average star will never become hot enough to support further fusion. Instead, once the helium in the star core is depleted, the star explodes, ejecting the outer layers of gas and leaving behind a white dwarf. This process is known as the planetary nebula. Then, only a small core, largely made of carbon and oxygen, remains after the star outer layers are lost. A white dwarf is the name of the star. Here, a body around the size of the Earth contains the mass of an entire star core. The pressure from the quickly moving electrons makes it feasible for such a tiny size to exist. Only stars with cores smaller than 1.4 solar masses, like the F star, will suffer this destiny. These stars like white because they are burning. So, the black dwarf is the final stage in the life of the F star. They are the remains of white dwarfs white dwarf that have gradually cooler and dimmer as house the remaining few. They will eventually run out of oil and fat until they are no longer visible to us. So that's all from us. I hope you guys can enjoy listening our presentation. Thank you.